again, you have domain. You discretize it by square grid. Delta is just half the diagonal of the size, half the diagonal of a little square. And we are interested in computing the limit of this once we subtract off the 1. And we're interested in showing that this converges to something. Okay? I won't recall what the something is. It should appear in the calculation later. So, what have we done last time? We've introduced a function f omega delta a z, which lived on the double cover of the domain ramified around A, and was defined as follows. It was defined as 1 over z sigma A times the sum over collections of pictures in a set gamma z of e to the minus 2 beta number of edges in that picture. Well, maybe something I should have reminded you is that this beta is beta critical, which is half of log root plus 1. Yeah. Exponentials of minus I times the winding of the path that goes from A plus delta over 2 to Z over 2 minus 1 the number of to the number of loops surrounding A times a sheet term S gamma AZ. So I assume that you have an idea of what these terms are. Well, just for concreteness, Z sigma A is the sum over all collections of pictures with no path of exponential of minus 2 beta number of edges in there minus 1 the number of loops. Okay. So gamma is the set of omega such that they form loops. Gamma z is the XOR of any omega there with a path gamma z. And what should I add? So omega is in gamma, and gamma z is a path from A plus delta over 2 to z. Okay, so that's the setup. A is here, z is somewhere there, and that's what we have. Okay, so what we did last time is we made some statements. We stated first that this thing had a connection with the quantity of interest. Okay. Namely, if you take this function here and you evaluate it at A plus delta over times 3/2, so you evaluate it here, then it gave you the quantity you were interested in. Okay. Then we had some boundary conditions. About the argument of the function. Let me not write them explicitly. For now, so we had some boundary conditions. And finally, and most importantly, we had S holomorphicity on the domain, except at the source point where we decided it was best not to define the function at all. Okay. So those are the things we had. Let me just remind what S holomorphicity is. I made a small typo last time, so it's the occasion to correct it. So the definition was F is S holomorphic if for any Z mid-edge, for any adjacent incident vertex in adjacent corner C, so for any corner C that is next to Z, for any Z between them somehow, vertex V between them, the picture is as follows. You have your squares, you have a corner C, you have a vertex mid-edge Z and a vertex V, and the definition was that f of C equals 1/2 of f of Z plus complex conjugate of C minus V divided by C minus V modulus times f of Z. So the thing I forgot last time was this denominator. I wanted a complex number of unit length, so I should have divided by this term. Okay, so that's the definition. It was an exercise to check that the function defined as such at the critical value of beta satisfies this. It also was an exercise to check it implies discrete Cauchy-Riemann equation in the sense that if you take the value here minus the value there plus I times the value here minus the value there, you get 0. Or if you take the value here minus the value there plus I times the value here minus the value there, you get 0. Yeah? Why this relation should be satisfied? How you prove it, you mean? Or how you guess it? That's a good question. I mean, it's a really good question. How you end up guessing things in this way? Okay, so what this means is something about a projection of some values of the function. So let's take a concrete example. What does this relation mean in this picture? Okay, in this picture, what is C minus V divided by norm of C minus V? Well, it's simply 1. Okay? So it means that f of C is just the real part of the value there. Okay? So that's what it means here. Now if your C is there, for instance, and your Z is there, then actually the value here is the imaginary part of the value there. Okay? If you take the value, if you look at the value here, for instance, it's going, well, the value there is a bit easier to first. If you compare the value here and the value there is the average of the real part and the imaginary part somehow of the value there, the complex average. So you take real part plus I times imaginary part of the two, and that's what the value here is relative to the value there. So now it can be checked that these relations are essentially equivalent to the prescription that the value on these types of corners should be purely real. But the values on those types of corners, the corners that point west, should be purely imaginary. Well, there's a similar prescription for the corners of type south and north. and that actually it is equivalent to have these relations to having the relation that the restriction to the so-called real part, the corners of type east, is discrete harmonic, and that together with the so-called imaginary part, the corners of type west, it is actually discrete holomorphic. Okay, so now there are a few questions you can ask. Why do we phrase it in this way? Well, because that's the way in which it is the easiest to check. And how could one guess what this definition would be? So it is fairly intuitive that some relations should be about the argument of some function, that we cannot really decide that the values are the same, but that we can say something about the arguments of the function, about some projections or something like that, because we have a complex factor in terms of the winding. And the winding, well, really depends on the corner on which, at which you look at. And somehow, if you hope to find some relations between values of the function, this winding suggests that there is something about, some complex directions that is satisfied, and that's how somehow you can guess this. As to the very history about how this notion was found in terms of projection, I don't really know. It has it's not the only way in which you can formulate things. The reason we formulate things in this way is because it makes things much more convenient and much easier to explain. But I must say I don't really know somehow how this notion, which as written as such was introduced by Smirnov, came to prominence. That it's technically equivalent to other notions which maybe are easier versions of discrete holomorphicity. It was known for a long time that Ising model satisfies some relations of this form or another form, or closely related forms. But why one has this form, this very form? I must say I don't have a single, simple, and complete explanation. So, but it's a good question. Okay, so it can be checked that this implies discrete Cauchy-Riemann equations in the sense I wrote, and it can be checked, and that's important for us. But it also that the discrete Cauchy-Riemann implies discrete harmonicity. It's going to be important for what I want to present now. So what does discrete harmonicity mean? It means the function satisfies a discrete analog of Laplace equation, which is Laplacian equals 0. How come? What does it mean? Well, it means that, for instance, the value at the vertex here is the average of the value at the 4 vertex I'm surrounding with a square. Okay? It's very simple. The value here is the average of the 4 values there. Similarly, the value here is going to be the average of the 4 values there. Okay. So again, it's fairly easy to check. Well, it follows from the definition of S-homomorphicity if you believe that the observable satisfies it. It's very easy to check on the definition of the observable of this function that on the corners of type east, the function is purely real. You can check the only complex term is the winding term, and you can check that the winding will not do anything but a multiple of 2 pi. So in the exponential, complex exponential, you're going to get a real number. So it's easy to check that the function on these corners is purely real, and that discrete Cauchy-Riemann implies that discrete harmonicity. Okay. So I'd like to make a small comment at this point. In principle, you can check directly discrete harmonicity at the level of the corners. You could check in principle that the value here is exactly the average of the 4 values there. But it's a bit complicated, the calculation to do. As a matter of fact, I don't know anyone who's carried out this computation to the end. It's in principle possible because it's true. So If a combinatorial statement like that is true, then it can be checked. But it's not very convenient because it would involve lots of values of the function in between to prove it, and it's much more convenient to rephrase this, the relations that this function satisfies in terms of this discrete holomorphicity, which involves really close by vertices. Okay. So we have that our function is discrete harmonic wherever it needs to be. Okay, so now fine. We have something. We have a function at a point. It gives us a value of interest. It satisfies some boundary conditions and it satisfies some relation that imply discrete harmonicity. So it seems that we are in good shape to prove convergence of something. Okay, and as a matter of fact, we are. But a priori, it's not completely obvious, whether this function should converge or whether a renormalized version of it should converge. So how to guess what is the right order of magnitude of this function as the mesh size goes to 0? How does it behave in the limit? How to guess that? So for that, we will do something which is a bit different from what has been done for percolation. Well, I mean, for percolation, it was obvious that the function we introduced, if it is the relevant object, has the right scaling because it's a probability of some event that has non-trivial probability. So it's obvious you should not magnify it or de-amplify it. But here it's not obvious that the function we introduced has the right order of magnitude. As a matter of fact, it doesn't. We need to renormalize it to pass to the limit. So how are we going to do this? How are we going to guess what is the right order of magnitude? Okay. So the way we're going to guess is as follows. So that's really the way we guess when we did this project. So you ask yourself the question, okay, maybe I don't really know what it means for delta to go to 0. I mean, what's going to happen, but I can guess what's going to happen, not when delta goes to 0, but when the domain, discrete domain, becomes bigger and bigger, okay, tends to the whole plane, whole square lattice. So it would be a slight problem to define this function on an infinite discrete domain, because you certainly would have an infinite sum in the numerator and in the denominator. So it's not completely clear this sum exists, or it can be given a meaning, but we can still guess. It's totally fine to guess what should happen. So what should happen? Well, we know a few things. There is one value that we know better than the others. Somehow it's this value, okay? This value is the ratio of these two things. Now, what should that ratio be when the domain is infinite? It should be 1. It should be exactly 1. There should be absolutely no difference between the value of a spin at one point and the value of the spin at the next point, because it's translational invariant once you're in the limit. So again, it's technically a problem to write directly omega delta is the whole plane, because the expectation, the numerator and the denominator are both 0 when the domain gets infinite at critical temperature. But okay, we can still guess it has no, it should really be 1. So we guess that f of the whole plane at a plus 3 delta over 2 should be 1. Okay. That's a reasonable guess in the sense that provided there is an infinite volume limit, that's what you should get. Now, there's a little magic trick that you can guess if you think for a while about that. It's okay. So now we have a function. We imagine our plane. Now we are in the infinite plane. So we somehow know this value. We declare that there should be a value that's 1 here. Now, do we know that value, for instance? Well, in the discrete domain, we don't know that value. But in the whole plane, we know that value. Why? The idea is that you can see there's some cancellation going on, because say if you were in the whole plane or in any symmetric domain for that matter, what you would have is that somehow half of the pictures would come with a path going this way, and the other half of the picture would come with a path going that way. I mean, more precisely, for every picture coming from above, with a path coming from above, there's a reflected picture with a path coming from the bottom. So now, how does a reflection affect the weight of a picture here? Well, what you can see is that, say, let's do an example. If, say, if I look at this picture, for instance, the winding is pi. Now I reflect the picture. The winding is minus pi. Okay? So what happens? So is it? No, it's not. No, I'm sorry. I said minus pi. I meant 2 pi and minus 2 pi. Sorry, apologize. Okay. So so here you have e to the minus I times either 2 pi over 2 or minus 2 pi over 2. It doesn't change anything here. However, well, here it doesn't change anything. The number of loops is obviously preserved. Number of edges obviously preserved. But this term will be different, because it's really, I mean, it's really like when you try to construct the square root function, and you declare square root of 1 is 1, and you make a turn here, and you arrive at square root of 1, and you declare it's I. But if you do it in the other way, if you declare the square root of 1 is 1 here, and you say, okay, now square root of e minus pi I over 2 is e minus pi I over 4, square root of I is e minus pi, or square root of minus I is e minus pi I over 4, and you arrive here and you declare that the square root of minus 1 is not I, but it's minus I. You try to define the square root continuously in the other way. So there is clearly a sheet problem here that if you go in one direction and the other direction, you end up with a different sign. And that's exactly what this sheet term is measuring. Whether the point here is on the same sheet as this point as viewed when going along that path, or whether the point here is on the same sheet as this point when going along that path. So this point, once you fix a z, for half of the paths it will be on one sheet, and the other half it will be on the other sheet. So the result is that all the terms here are the same except this one, which is the exact opposite. So everything cancels. So we guess that f c delta a at what vertex? What point? Well, this is a minus delta over 2. But the same argument will work for here, for a minus 5 delta over 2. So a minus delta over 2 minus 2k delta will be 0 for every positive non-negative integer k. Okay? Well, that's good, because now let's look at what we have. We have a function which is, you know, if we start trying to guess what will be the limit, we have a function that is going to be 1 here, 0 here, 0 here, 0 here, 0 here, etc. And if we restrict to the corners of type east, I mean the corners we are looking at right now, we have a harmonic function which we know, okay, is defined on this double cover, whatever, but on the whole half-axis is 0, and just at the tip of this half-axis it's 1. So what is that? That's really the probability that a random walk in the domain, and that is stopped when it hits the axis on the left of A, hits actually the A, I mean, hits the tip of the half-axis. So we deduce that this thing, which again we don't know exists, but we can postulate exists, restricted to corners east corners is actually the probability as a function of corners 3 is the probability that a simple random walk in C delta minus A minus the positive. So you take the plane, the discrete plane, so the square grid, and you remove all the points that are on the left of A. Okay. Hits A minus delta over 2 before any A minus delta over 2 minus 2k delta with k positive. Okay? So we have a random walk that will live on these corners. And so it's just a random walk that jumps on one of the 4 neighbors, like that. Simple random walk. And you look at the chance that it hits, hits A plus delta over 2, that it hits this guy, because the chance is going to be 1 here, before any of the other guys. So maybe it's better in this picture. The chance of hitting that point before any of those points, because here it's 0. Okay? So the reason is we have a harmonic function which is equal to 0 on this point, equal to 1 on this point. There's only essentially 1 that decays at infinity. We postulate that we decay at infinity. You know, at this point, we're just doing exploratory analysis. We can totally guess, non-rigorously, because we just want first to guess the right thing. So it should be, as a matter of fact, it is true that it will be that, but somehow we don't really need this at this point. So, okay, good. Now, random walks, we know a bit better than this complicated function. So how are you going to guess what is the right scaling? Well, at this point, we can guess. Okay, so say if I take this quantity for random walks, how should it scale? Well, I mean, and what should be the limit? Okay, let's first guess what the limit should be. So we can guess that the scaling limit. So now we are making delta go to 0 after we make and the domain go to the whole plane. Should be. Well, let's write it with a lowercase. So it should be a function defined on the whole plane, complex plane. Now it should be holomorphic. Well, the reason why it should be holomorphic is because it's discrete holomorphic on the lattice level. So again, assuming that things go well, we get that it should be holomorphic, and that it should be 0 on the whole axis on the left of A. It should not be a trivial function. It should decay at infinity, and it's probably going to be fairly big, just on the right of A, because we're going to have rescaled in a way that will make things not go to 0 in the scaling limit. So what we obtain is that the real part of this function should be the real part of the right-hand side. Because if you look at the real part of this function, satisfies all the things it should satisfy. Okay, the real part is going to be 0 on the axis on the left of A, because that guy is going to be purely imaginary. It's going to have a singularity at z equals A. When you come from the right, it's going to be very big. If z comes to A but from the right, it decays at infinity, has exactly the right behavior. That's what your guess is, and that's the right guess. Okay, so now, how do you scale a function so that it scales this way? Well, it's a bit of dimensional analysis to guess, but that's not very difficult. So you can actually guess that the way to renormalize should itself involve a square root. So this way, we guess C delta A should be renormalized by a function theta delta with theta delta behaving like 1 over the square root of delta as delta goes to 0. And actually, that's not something we need in our paper, but some students of mine proved. So S.C. Park and Reza Gesari, they did an internship with me, and they proved actually that the right way to rescale is this one. Somehow it helps for concreteness, but it's not technically necessary for the proof. So they proved that you can choose theta delta to be 1 over pi times delta. So the statement, 1 over square root of pi delta times this function converges to this function. Okay. Somehow we postulated that this function existed. Then we kind of constructed explicitly its real part with a simple random walk, and then we can extend it to all the points of the lattice, not only the corners of type E, in a unique manner. So you get this result. So now we guess that you should also renormalize the function on a bounded domain in the same manner. Okay, that's very reasonable. There's no reason why you should renormalize differently for a domain or another. Should converge to. Okay. Okay, so that's a good guess. That's a correct guess. Now, how do we prove convergence? So after all these guesses, how do we prove convergence? The idea is that we say, okay, there is one function we know converges. It's this guy if we postulate a good definition for it. We don't really know if we can make the limit omega delta goes to the whole plane, but we can certainly postulate what it should be. It should be something related to random walks. It should be a discrete version of this guy. So what you see at this point is that there is something fairly obvious, is that something, quite bad happens as z equals a. I mean, this is obviously a singularity. Okay? And it's a fair guess to think that this problem is related to the fact that we chose not to define the function just on the right of the thing, just on the right of the point A. We chose not to define it, and that's probably related. I mean, what it actually meant that we didn't define it, and that I couldn't define it later, is that there is no way to define it here in such a way that you still preserve this S holomorphicity everywhere. If you forget about the point, then you can still be S holomorphic everywhere else. But here you have no way to assign a proper value that will make it S holomorphic everywhere. Well, in the limit, it should not be holomorphic as z equals a. So since this point informally is collapsing on to that point, it's reasonable. There is a problem here. Okay, so there is a problem, but the good news is that this problem for f omega delta might be exactly the same as the problem for fc delta. This guy might have a problem at z equals a. I mean, it probably has the same problem as this guy, because this guy is the postulated limit of that guy. So now what you can do is you can say, oh, actually, what if we look at f omega delta a minus fc delta a? Yeah. Somehow you kill these two guys have problems. You maybe don't want to know what the problems are, but you have a good reason to assume that the problems are the same. So they kill each other, okay? Can be extended as holomorphically to to z equals a plus delta over 2. And what is the value there? Well, if you're really lucky, and you are, and the value there should be 0. Will be 0. Okay. Will be 0. Is 0. Okay, so there you need a bit of combinatorics to check that if you assign the value 0 to the function that is the difference of the two functions, then it's a consistent in the sense that you are still S holomorphic with everyone else. So that's good somehow. At least we have killed the singularity. Now we would like to prove convergence of this difference once you renormalize by 1 over square root of pi delta. So that's yes.
How do you define F C delta?
Okay, so it's a bit complicated, but it's nice. So the idea is that I guessed some values of it, and at some point I guessed enough values plus I guessed the harmonicity that it would be completely defined by it. Okay, I guess the value here should be 1. I guess the value there should be 0. I guess it should be discrete harmonic. That actually, and I guess it goes to 0 at infinity. That defines uniquely a function. And I don't need to know that this function is actually the limit of this guy. I just need to know that it has exactly the properties it should have. And suddenly you can, basically you construct first its real part with random walks, and then you do a completion of all the other values. There's a unique way to complete all the values at all the points, such that you keep the original values and you are holomorphic. It's a bit complicated when you need to do complex conjugation and preserve monodromy, etc. But you can do it. That's the idea. Okay? Thanks for the question. Okay, so now we have an artificially constructed function, but it should have exactly the same features as this one. So they kill the singularities, and so it extends as holomorphically. So you can think, well, now I'm in good shape for proving convergence. And somehow it's true, but there are more subtleties along the way. So I just want to mention one, because I think it's kind of cool. So the idea is that, okay, it has no singularity on discrete level. However, there is a potential problem, which is that singularities, when you have this ramification, they might still arise in the limit. Even if you don't see them in the discrete level, they might arise in the limit. And so we had really hard time controlling this, but we found a trick, the reflection trick. The idea is that, okay, we need to have more control on our function. We have some control. We know that it at least has no discrete singularities, so no obvious obstruction to convergence, but we need a bit more. And the reflection trick is to do the following. You have your domain, your point A, and what you do is you look at the reflection axis. I mean the real axis, the axis parallel to a real axis passing through A, and you reflect your domain. Okay. Okay. So omega tilde, the domain omega reflected with respect to A plus x for x in R. And so now what you can notice is that f omega delta A plus f reflected domain omega delta A. Well, we had an argument saying that some things cancelled on this half axis. That was on the basis of reflection. Now, if you add a function to the function defined on the reflected domain, has cancellations on A minus x for x positive. Okay. So that's by symmetry. And the small miracle is that the difference also has some cancellations. has cancellation. Not on this axis, but on the other axis. On a plus x positive. So somehow you rewrite this guy as the average of this sum and that sum, both of which have different cancellations. And these cancellations are nice because at least they tell you that, you know, on a good half-axis you're 0. So if you're 0 on a half-axis, you can really forget about this double sheet thing. You can just say, well, okay, now I'm going to make a cut precisely on the axis where I'm 0. I'm going to say that's part of the boundary now. Now I have a new boundary condition, 0, on a cut, you know. Now I'm going to be able to say, okay, on this part of the domain, I'm just 0. So that's, you know, my domain becomes simply connected without no branching because I just cut things here, and the new boundary value is just 0, very nice value, it will not cause any blow up. And I need just to control what happens on the boundary, okay, on the rest of the boundary. I need to control what happens there, that it doesn't blow up. So the way we can control things don't blow up is using the boundary conditions. So it's a bit complicated, actually, so I won't really go into the detail of how you control things. Let me just somehow say, okay, at this point, use boundary condition to control the size. Harmonicity to control the variation. The idea is that if you have discrete harmonic functions and they are bounded, actually, you know, they don't wiggle in a crazy manner inside. Because you're the average of your neighbors, you cannot just say, I want to be very big or I want to be very small. You have to you know, be compliant with your neighbors, and so basically, the only bad thing that can happen to a harmonic function is that some points blow up. But if it does, if it's not the case, if nothing blows up, then actually your derivatives are also controlled. The derivatives of your derivatives are also controlled, and you can really prove a priori that if you have a limit, and that you should have a limit, and that if you have a limit, it's infinity. That's very easy, and actually it's even holomorphic in our case because you can bootstrap these Cauchy-Riemann equations. So we control the variation, and now let me tell you what is the function here, and the limit. Is uniquely identified by holomorphicity, singularity, and boundary conditions. So what is this limit? We don't really need to know what is the explicit formula for the limit. What we care about somehow is understand how it relates to the conformal structure of the domain. So I'll be really quick on this subject now. I still want to mention a bit facility. So this guy has a unique limit. It can be computed explicitly, basically, and the limit is this guy. Okay, it's a limit holomorphic function. It has a branch around z equals a, but it's normal that it should behave in the limit, the first order like this, like that function, and has a correction here. It's not the same as the other function, so it has some number here, and the a. The nice thing is the real part of a is going to be exactly the quantity we were looking for. So I mean that somehow at this point it's just an observation that you have a holomorphic function that satisfies the continuous analogs of all these guys, and it's uniquely identified by that, and should have this Stato expansion. And somehow magically you observe that this a here is the dx of the log. Actually, imaginary of a which is minus the dy, the y derivative of the log. Even though we don't need that, it's always interesting to see. So if you move in the vertical direction, you get minus the imaginary part of a. So now, why is it that we obtain these things? I mean, why is it that the formula suddenly pops out here like that? Well, the reason is the following. So why? So obviously we have something at first order and something at second order. Well, the idea is that if you look at this guy, this we said it's 1 plus delta times, well, something. Let's call it a delta plus small of delta. That's what we try to prove. And what we had is that the function f omega delta a at a plus 3 delta over 2 was exactly this ratio of expectation. So now the idea is that if we take f omega delta a and we subtract fc delta a, the full plane discrete thing, which we postulated was 1 at the point, you evaluate this here at a plus 3 delta over 2. You get the ratio of expectations minus 1. So something that goes to 0 as delta goes to 0. But what you can hope is that, okay, now if you take 1 over delta times this, you get 1 over delta times that. And now, maybe as delta goes to 0, you get what you want. So how are we going to be able to read that in the continuum? Well, the first thing we should do is take, there's an extra 1 over square root of pi delta. No, that's right. That's right. So now you ask the question, okay, now how am I going to be able to read that in the continuum? So I have the function f omega, little f omega, and I have the little function fc here. So if I want to mimic this local expansion around the singularity, I should of course take this minus the other guy. So I take this minus the other guy. It kills the singularity, as it should, and you get a new term here. Okay? And this term, if you evaluate at z equals a, is 0. Somehow, as it should, in the same way as if you take the difference and you go to 0, at first you get 0. But now you want to inflate again the thing that goes to 0 to see, you want to magnify it, to see this 1 over delta thing. So what you should do is you should magnify this thing by 1 over square root of z minus a, okay? For the same reason as, you knew that if you divide by square root of delta, you do converge elsewhere. And now you want the 1 over delta, so you need to add an extra pi over square root of pi over square root of delta to get the 1 over delta. Okay, you know that we have a scaling limit for the function with the 1 over square root. Now you'd add an extra square root to get the local behavior. So now here you need exactly to add also an extra 1 over square root. So you add an extra square root to the difference of the functions, and you get this term, and you identify. So it's a bit complicated. I don't want to go so much more into detail because I want to speak for 5 minutes about SLE, as I promised. But I hope at least you have an idea of how things work. I'll just summarize one more time. We have connected the discrete world using quantity with the discrete holomorphic world, this function. We have extracted a number of features on this function that actually identify it uniquely. It has boundary conditions, it has the right value at the right point, and it has a holomorphicity. So now you can hope that it has a scaling limit. So first, in order to hope, you have to make your hope precise. So you first make a guess of what the scaling limit should be. And for that, you guess what happens if the domain goes to infinity. Actually, if the domain goes to infinity, you have a unique guess for what the function on this discrete level is. And this unique guess tells you actually a unique guess for what the limit of the full plane function should be. Once you're in this business, you understand what happens with the full plane. You try to apply the same recipe to the discrete domain. And so you subtract the thing you already know that causes some problem, and it kills off some of the problems. In order to kill further problems, you use a reflection trick, which adds further cancellations and makes the situation better. Then you use the boundary conditions to control the size of your function in a way I don't have time to explain. But you control your function. You control your function, so it must converge to something. Once renormalized in the way you guessed in the full plane, it converges to something. This something is identified uniquely by the analogs of these conditions in the continuum. You Taylor expand your function, and you observe, oh, wow, okay, here the second coefficient is just what I need. So how you make the connection between the second coefficient and what I need? Well, you reflect upon what happens if you look at this ratio of expectation, and what happens in particular if you try to extract this coefficient. How would you extract it? Well, you would first subtract the singular term and then re-amplify what you have and approach again the monodromy. So here you do exactly the same. You take this thing, you subtract the full plane thing, and that has the amount of subtracting this one. But this is an obvious term, and so there's an obvious term here. You subtract it, and you amplify, and you amplify by by an extra 1 over square root, and that really amounts to amplifying by 1 over square root in the continuum. So limits don't quite interchange because constants have wrong if you do that, but morally they do, and that's what we usually use. Okay, let me really quickly discuss the SLE thing. I won't have the time to do the calculation. I'll just explain, what is the idea, how the results we proved about Cardy's formula or spin allow you to actually get SLE. So back to SLE. Oh, not back to, but yeah. So I'll be fairly quick. So the idea is that, okay, interpolation, as you probably have seen in Vincent's class, if you can color here at black faces on the boundary, and you can add white faces on the boundary. Okay. So your hexagons are colored black and white. Everything is independent, so adding this boundary condition doesn't change anything inside. And so you can draw an interface that has black on one side and white on the other side. It's a random interface because it explores the configuration, and that's random. And so you'd like to prove that the scaling limit is SLE. And the claim is that Cardy's formula is the way to prove that. So why is it true? Why can we just estimate probabilities of crossing to prove convergence? So convergence proof. So first, you use RSW to get some regularity on the curves. On the curves, meaning the interface. Well, you want to make sure your interface doesn't do anything crazy, like something like that. You want to avoid that, okay? So how can you avoid that with Russell-Sam or Welsh? You can say, well, with the fair chance there's a crossing here, with the fair chance there's a crossing there, at least small crossing. And so your interface has to be stuck between these two. I mean, that's really not the way to write it properly, formally, but that's the intuition, and this is not very far from how you write it properly. So the idea is that, things happen there, and, you cannot do whatever you want. There are chances against you if you want to do crazy things, and so you don't do crazy things, or not too crazy. You're still fractal in the limit, but you're not completely crazy. So you get Hölder subsequential scaling limit. It's called the Eisenman-Borchardt theory or result. Eisenman-Borchardt. Now you have your, take a limiting curve. Take a limit. Why is it SLE? Okay. So let's first answer the question morally and then a bit more technically. Why is it morally SLE? So the idea is the following. So you know a bit of your curve here. You fix an extra point, say, here. Let's add a point Z. So add a point Z on the boundary. Somewhere on the boundary, it doesn't really matter where. Let's say we add it here. Okay, we add a point Z here, and we ask the right question to the curve, or to the configuration described by the curve. You ask the question, what is the chance that there is a black crossing doing this, linking this? Well, you add 2 points actually. Add Z and W. Well, you can do it whichever way you want, but add 2 points. I have a point W here and a point Z here. And you ask the question, what is the chance that there is a black crossing linking that thing to that thing? So let's write what this means. Let's call this point A and this point B. So ask probability of AZ linked by a black path to BW. Knowing it's the interface. Knowing the interface for a few steps. Okay. So knowing that on the discrete and then passing to the limit. So ask this quantity. Ask what is this quantity? Well, this quantity, as you guess, can be computed with Cardy's formula. So it's the same as probability that that the tip of the curve Z is linked to BW in the domain slit by the curve. Yeah. So if you look at the domain slit by the curve, if you know this part of the interface, what you know is that here, well, on the left you're black, and on the right you're white. So basically, what you know is that the chance that this happens, knowing the curve just tells you the colors of some hexagons, the colors of the hexagons on the right and on the left of the curve. So this initial segment of the curve becomes part of the new boundary. So knowing the curve is just knowing your domain is smaller and that the boundary conditions are the right ones. Okay. So now the thing is that this is a martingale. Why is it a martingale? Well, because it's expectation of an indicator function knowing some filtration associated with random variable, and this filtration is obviously growing in time. It's martingale in time. But what you know is that this converges to Cardy's formula. The probability is described in terms of this mapping to an equilateral triangle. So in the end of the day, and I'm really done in the next board, what you do is the following. Your curve grows in your domain. We're going to prove it's SLE. How is SLE defined in the domain? It's defined as the image of SLE in the half plane. Okay. So you map this to the half plane. Now you have a curve that grows here. When I prove that this curve in the half plane is SLE, how do you prove it's something is SLE? What does it mean that some curve is SLE? Well, described by Loebner chain. And you know, a dgt is equal to 2 over gt minus ut. I mean, it can always be done. Well, can be done anyways. If your curve is not too crazy, you can always find the ut. And now the question is why ut is square root of 6 times Brownian motion. That's what it means for the curve to be SLE. So why is it the case? So how are we going to be able to control how this ut moves? The idea is as follows. You know, your ut wiggles, and somehow you're able to detect some signal using the fact that this is a marking curve. More precisely, what does it mean? Well, it means, you know, okay, the way ut wiggles can be plugged into the Cardy formula. Can I be more precise here? Yes, I can be more precise. I'll just be a bit more precise. So the idea is that morally, this is still your percolation interface. So this was your percolation interface. So in any domain, with any mark point, and any initial segment of the curve, you have a formula for the crossing probability, because that's exactly Cardy's formula. Okay, you have a formula, and no matter what ut does, you can keep track of how the probability has changed. In principle, in practice, you can. Okay, if ut moves a bit on the right, how has it influenced the chance that there's a crossing? If it moves to the left, how has it changed? Well, you can compute all of these things fairly explicitly because the Cardy's formula is particularly nice and defined in terms of conformal mappings, and all these SLE is defined in terms of conformal mappings. So you can really study how the u sub t makes this probability change. Now what you know is that as the curve grows, as the time passes, this probability behaves as a martingale. And it gives you some information about what ut can do. And what you get in the end of the day is that ut must be a martingale itself. Yeah. So it's already quite good. But there are less objects that are just martingales. So the idea is really that this guy has to move in a kind of balanced way for the Cardy's formula to move in a balanced way, and it should move in a balanced way because it is a martingale. Okay, and if you study second-order effects, you also get that typical Ito type thing. You get that also. This also is a martingale. For this, you need explicit formula. Huh? And if you have these two things, you have a theorem of Levy that says that u sub t is the square root of 6 times p. Okay, so that's more or less the idea. Okay, so you keep track of a quantity that you can compute explicitly for every domain and a collection of free parameters like w and z. You keep track of this quantity as the interface grows, and you know that it behaves like a martingale, and you use the explicitness of your information to relate the way u sub t moves to the way the quantity moves. And if the quantity moves like a martingale, it gives you constraints on how u sub t must move. These are the constraints for percolation, and that's how you get the result. For Ising model, it's very similar. A proof that has never been written, but maybe it's the conceptually nicest, is you can look at, okay, what is the value of a spin with the expected value of a spin with plus minus boundary condition. Again, you can make an interface for Ising that separates minus from plus, and this quantity, this expectation of the spin, will behave like a martingale as the interface will grow. And using the explicit formula, you get for that the limit of this quantity, which we obtained essentially in this manner, you can again do the same thing, and the only difference is you will get a 3 instead of the 6 here, and you will be done. Okay, thank you very much.
No, I mean, okay, so maybe what he's doing is the proof to convergence is yeah, sure, but not with that by marking it. It's alright, that's somehow it's the most natural. Yeah. Yeah, so